In 2017, a team at Google dropped a paper with a title so bold it was almost audacious. Attention is all you need. And you know what? They were right. This single paper completely rewrote the rules for artificial intelligence and language. It's the foundational blueprint for pretty much every major AI we use today, from ChatGPT to Gemini. So let's break down the paper that literally changed the world.
For the longest time, this was the big question, the one that kept AI researchers up at night. Human language is just so messy, right? Words change their meaning all the time depending on the context. You've got sarcasm, you've got idioms, you've got these long, complicated sentences where the beginning connects to the end. So how on earth do you get a machine to grasp all of that? Well, that was a challenge.
All right, here's our game plan. First, we're going to look at the old way of doing things and the huge problem it had, what we'll call the sequential bottleneck. Then, we'll dive into the elegant solution, the power of attention. From there, we'll introduce the radical new machine they built, the Transformer, pop the hood to see how its engine works, and finally, look at the mind-blowing results that kicked off the AI revolution we're living in right now. Okay, so first up, let's set the stage. Before this paper came along, if you wanted an AI to understand language, you'd probably use something called a recurrent neural network or an RNN. And these things had a big fundamental flaw in their design.
The best way to think about an RNN is like someone reading a super long scroll. It starts at the first word, processes it, then moves to the second, then the third, and it tries to keep a running memory of what it's just read. But just like you or me, its memory isn't perfect. By the time it gets to word number 500, it's probably forgotten some really important details from word number 1. The paper calls this the inherently sequential nature, and it was a massive bottleneck holding everything back.
Now this chart, taken right from the paper, shows you the problem in black and white. For an RNN, the number of steps it has to take, these sequential operations, goes up with the length of the sentence. That's what O of N means. Longer sentence, longer wait. And the path for information to travel between the first word and the last word is also really long. But now look at the self-attention column. Everything is O of 1. It's constant. That means it doesn't matter if the sentence is 10 words or 1,000 words. It can connect any two words in a single step. This wasn't just an improvement, it was a total game changer in efficiency.
So, if reading words one by one is the problem, what's the fix? The authors of this paper pointed to a powerful idea that had been floating around, a mechanism called attention, but they decided to take it to the extreme.
And this is the magic trick right here, self-attention. Instead of that slow, linear, one-word-at-a-time process, self-attention gives the model the ability to look at every single word in the sentence at the exact same time. For any given word, it can instantly see how it relates to every other word, no matter how far apart they are. It's like creating a complex web of connections, a map of how the whole sentence fits together, all in one go.
Armed with this supercharged version of attention, the researchers didn't just tweak an old model. Nope, they threw out the old designs and built something completely new from the ground up. They called it the Transformer.
I just love this quote from the paper's abstract. It's so confident. They're not just adding a new feature. They're saying we're throwing out recurrence, that whole one-word-at-a-time thing, and we're throwing out convolutions, another popular technique. They made a bet that this one mechanism, attention, was all they needed to build a state-of-the-art model.
And this is it. This is the diagram that launched 1,000 AI startups. It might look a bit intimidating, I get it, but this is the blueprint for everything, from Bard to GPT-4. You've got two main parts, the encoder stack over on the left, which is responsible for reading the input, and the decoder stack on the right, which is responsible for writing the output.
So, let's simplify that flow. Think about it like a translator. First, the encoder's job is to read the whole English sentence. It uses self-attention to figure out what every word means in the context of all the others. It creates a rich numerical representation of that meaning. Then the decoder takes over. Its job is to write the German translation one word at a time. And for each new word it writes, it pays attention to two things: the full understanding from the encoder and the German words it's already written.
Okay, so that's the high-level view. Now for the fun part. Let's pop the hood and take a look at the specific gears and pistons inside this thing that make it so incredibly powerful.
This is probably the clearest, most intuitive example of self-attention at work. Look at that sentence. What does the word "it" refer to? The robot or the ball? Now, for us humans, that's a no-brainer. But for a computer, it's ambiguous. This is where self-attention shines. When the model processes the word "it", it calculates an attention score to every other word. It sees a super strong connection to ball and a much weaker one to robot. And just like that, it correctly understands that the ball is the heavy thing. It resolves the ambiguity instantly.
And this is the machinery that makes it happen. On the left, you've got the basic building block, what they call scaled dot product attention. That's the core calculation. But the real breakthrough, the genius move, is on the right, multi-head attention. The researchers figured, why ask one attention mechanism to understand everything about a sentence? That's asking a lot.
So instead, they built a team of specialists. Think of multi-head attention as having, say, 8 different attention heads, all looking at the same sentence at the same time, but each looking for something different. You might have one head that's basically a grammar expert. Another one is laser-focused on tracking who the subject and object of the sentence are. And a third one is the pronoun expert, figuring out what words like it and they refer to. When you combine all of their findings, you get this incredibly rich, multi-layered understanding of the sentence that a single head could never achieve on its own.
Okay, so there's one last puzzle piece. If you're looking at all the words at once, how does the model know that the dog bit the man is different from the man bit the dog? The word order is crucial. The paper's solution is so elegant: positional encodings. Before the model does anything else, it stamps each word with a little bit of extra data. Think of it like a GPS coordinate that tells the model its exact position in the sentence. It's brilliant. You get the speed of parallel processing without losing the vital information about word order. So the theory is beautiful, the architecture is clever, but the real question is, did it actually work? Well, let's take a look at the results they published, because this is where things get really exciting.
This number right here, 28.4. In the world of AI research at the time, this was an earthquake. This was the model's score on a standard machine translation test from English to German. It's called a blue score, and it didn't just beat the old record, it absolutely smashed it. An improvement of over 2 full points on this scale is just massive.
But here's the real kicker. Look at this table. The transformer didn't just get a better score than the previous state-of-the-art models, it did it while being way, way cheaper to train. Look at that training cost column. The transformer achieved its record-breaking score using significantly less computation than its rivals. It was better, and it was more efficient. To put it in perspective, they got these results after training for just 3.5 days on only 8 GPUs. That was a tiny fraction of the time and money it took to train the older, more complex models. Because the transformer's architecture could be so easily parallelized, it made training huge, powerful AI models not just possible, but practical.
So in the end, this paper did more than just introduce a new model. It laid the foundation for the entire modern era of generative AI. Those core ideas, self-attention, the transformer architecture, they are inside virtually every large language model we talk to and use every day. The paper proved its bold title wasn't just a catchy phrase, it was a prophecy. And it leaves all of us with a pretty exciting question. Now that we have this incredible tool, what are we going to build with it next?